In today's video, we'll be talking about significant figures. After watching this video, you should be able to determine how many digits are significant in a value, be able to add, subtract, multiply, and divide using sig figs, and we're going to talk a little bit about scientific notation, just a little refresher on that because I assume most of you are able to put numbers into and out of scientific notation, but it goes well with sig figs, so we'll throw that in this lesson also, little bonus. So let's get right to it. Significant figures are those to be known to be reasonably reliable. Okay? Therefore, basically all measured figures and one estimated figure would be considered significant. Okay, ones that we can actually consider reasonably reliable is all measured figures and one estimated figure would be considered significant. So for example, let's say you throw in your calculator 52 divided by 2.3. Okay, and you do that, and you get this number. This is what pops up on your calculator. Okay, 22 point, a whole bunch of stuff. All right. You'll notice we have numbers in the millionth place, the billionth place, the trillionth place, and the quadrillionth place. Okay, and so you're telling me right now that you can vouch for this measurement to the quadrillionth place, okay? And that basically is crap, okay? You are not able to be that accurate, if you will, okay? So clearly we need to do a little bit in terms of what of these figures is actually significant and what is kind of a estimate, okay? Because to get a device that could measure into the quadrillions would cost you trillions of dollars. So here are some rules for sig figs. I know there's a ton of text on this slide, but these are rules that you can refer to throughout the course when you're needing to figure out how many sig figs there should be or how many sig figs there should be. So basically 5 rules. Digits that are always significant fall into one of these 3 categories. Any non-zero digit, okay, so at 2, 7, 8, you name it, if it's not 0, it's significant, okay. Zeros between 2 significant digits are considered significant. Okay, so let's say I have a number that is 9,009. Okay, these zeros right here are significant. Okay, because they're smushed between 2 non-zero digits. All final zeros to the right of a decimal point are significant. So if I put 0.00, these 2 zeros here would be considered significant, okay? Digits that are never significant would fall into these 2 categories. Leading zeros to the right of a decimal point would not be considered significant. They basically are what's called a placeholder. So for example, I have 0.002 centimeters, okay? In this example, 0.002 centimeters, the 2 is the only significant digit. Okay, so there's only actually one sig fig in that number. Okay, those zeros there are just placeholders. And then final zeros in a number that do not have a decimal point. Okay, so for instance, let's say I were to write down 5,600. Miles. Yeah, let's say I went for a jog over the weekend and I jogged 5,600 miles. All right. These zeros right here are not significant because there's no decimal point. The only significant digits in this answer is the 5 and the 6. Okay, so again, I know there's a lot of text here and I know there's a lot of rules, but this is something you can kind of refer to if we're ever dealing with things with sig figs and you need to have an answer that involves sig figs. So let's do a little bit of practice here. I've got 4 different values, okay, and I'm wondering how many significant figures are in each of these values. So for instance, 42.45 kilograms. How many sig figs are here? Well, I see a bunch of numbers that are not 0. And if you remember from the rules, any non-zero digits are always considered significant. So there are 4 significant digits in that measurement. Okay. 42.004 seconds, okay? You'll notice these zeros are smushed between non-zeros, and so that makes them actually significant, okay? Typically, zeros are not significant, but in this case they are because they are smushed between 2 non-zero digits, so there are actually 5 significant digits in this answer, right? Here we have 0.00654 amps, okay? The 6, the 5, and the 4 are non-zero digits, so automatically they are significant. So at the very minimum, we have 3 significant digits. But what about these 2 zeros here? Well, there is no number that's non-zero in front of them, and so they are actually what's called a placeholder, and so they are not significant, and so there are only 3 significant digits in this answer. And then here we have 3,300 meters. Okay, 3,300 meters. Any non-zero digits are significant, so the 3's are significant, so I have 2 at the bare minimum. But these zeros, they are not significant because there's no decimal point here. If there was a decimal point, then yes, we would be looking at significant digits. But they are not, or there isn't a decimal point, and so we would have 2. Okay, so that's just some practice. Once you get it, it's not so bad. At first, it may feel intimidating, but it's not so bad once you get it. There are 2 special situations that I would like to talk about that basically lead to you having an unlimited number of significant figures. Okay, so the 2 special situations, the first one is counted items. Counted items. Okay, so for example, if I count how many students are in this classroom right now, let's just say there's 23. 23 people would be an unlimited number of significant figures. Okay, so 23 is unlimited because there's 23 people. You're not really going to change that one way or another. Or 425 thumbtacks, or a dozen apples. Okay, I mean those items are counted, and there's no really discrepancy, if you will, between that answer. Exactly defined quantities would be the other special situation. And an exactly defined quantity would be something as like minutes. Okay, there are 60 minutes in 1 hour. Okay, so 60 minutes would actually have an unlimited number of sig figs because it's a defined quantity. There's no dispute about it. 60 minutes is an hour. Okay, or 1 hour is 60 minutes, vice versa. Okay, so those are 2 kind of special cases for counting significant figures. All right. Let's talk about significant figures and mathematical operations. And basically, there's going to be 2 different types of operations you need to worry about. Adding and subtracting, and then multiplying and dividing. So these rules are for adding and subtracting. Okay, so this would be the slide on adding and subtracting. The number of decimal places in the result, or your answer, the result, equals the number of decimal places in the least precise measurement. Okay, so what does that mean? Well, let's say you have this, 6.8 plus 11.934, okay? Again, if we look back at the rule, the number of decimal places in the result equals the number of decimal places in the least precise measurement. So this measurement right here is least precise because it only goes to the 10th place, whereas this guy goes much further beyond the decimal point. So our answer is going to be some number, decimal point, and then 1 number after it. Okay, so if you add this up, 6.8 plus 11.934, you would get 18.7. Okay, and you would notice there's 3 significant figures here, and we only have 1 number beyond the decimal point. Okay, and that was determined by this digit right here because it is the least significant digit, 6.8. Okay. For multiplying, it's a little bit different. Okay. For multiplication and division, it's the number of significant figures in the result equals the number of digits in the least precise measurement used in the calculation. Okay, so the number of sig figs in the result equals the number of the number of significant digits in the least precise measurement. And again, an example I think is worth 1,000 words. So let's practice here again. 6.38. How many significant figures are in this? Well, they're all non-zero, so there's 3. Okay, 3 sig figs in here. 2.0. Since this 0 comes after the decimal point and there is a significant digit before the decimal point, there are actually 2 significant figures here. Okay, so what's bigger, 3 or 2? Hopefully you all are thinking 2. And so our answer will only have 2 sig figs in it. Okay, so if you take 6.38 times 2.0 in your calculator, you should get 12.76. Okay. Now, I can't write 12.76. Why? Because I'm only allowed to write 2 sig figs worth. And so this is going to actually become 13 because this 2 gets rounded up to a 3. And so it's 13 because 1 and 3 are both significant, and so there's 2 sig figs right here. Again, I know this might seem complicated and intimidating at first, but it gets better as you do it and practice with it. Scientific notation. Okay, real quick rundown on scientific notation. It shows your value using the correct number of significant figures. So when you put something in scientific notation, the value you get is the number of significant figures in that answer. So basically your job when you're converting into scientific notation is you move the decimal point so that there's only 1 significant figure to the left of the decimal point. Okay, so it's going to be either like 3, 6, for some number, basically other than 0, that would be to the left of the decimal point. And show your number being multiplied by 10 raised to the appropriate power. Okay, so we'll do some practice problems to hopefully kind of help this sink in if you've forgotten what scientific notation is, or maybe just never learned it. It's not so bad. Okay, so here are some example problems. 234 million. All right. Now in this problem, I actually didn't write a decimal point, but it's like assumed to be here, and I'm going to move this decimal point to this spot right here, because if I move it here, I'm going to have one number to the left of it, the 2, that is significant. Okay, so this is how I do it. I don't know if you do it differently. I count how many spaces I have to jump to get to this point right there. Okay, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. So I made 8 jumps. Okay, so I have 2.34. And I don't write all these zeros, and the reason why I don't write those zeros is because they're actually not significant, because there is no decimal point there. But I have 2.34 times 10, and then I say how many jumps I did. Well, I made 8 jumps, so it's times 10 to the 8th. Okay, and that would be my answer, 2.34 times 10 to the 8th. Here's my decimal point right here. And I'm going to move this decimal point until I have one number to the left of it that is significant. And what number would that be? Well, it's going to be this 2 again. So how many jumps do I have to make to get it to that point? I'm going to go 1, 2, 3, 4, 5, 6. 6 jumps. Right? So I'm going to write 2.345, because those numbers are all significant, times 10. And then how many jumps did I make? 1, 2, 3, 4, 5, 6 times 10, and this time it's to the negative 6th power because I moved the decimal point to the right. So if you move it left, your exponent is positive. If you move it right, your exponent is negative. And when I'm saying exponent, it's this number up here. Okay. Now, some questions I could ask you would be like, well, let's take a number in scientific notation and make it just a number again, like these big old numbers here. So 6.54 times 10 to the 7th. What do I do with that? Well, this is my method to the madness, so you don't have to do it this way if you don't like it. I'm going to move this decimal point over 7 spots to the right. And so I'm going to make 7 jumps to the right. And so here we go. 1, 2, and so I've jumped over the 5 and the 4, and then I have 5 more jumps. 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7. And in these open spots, and I'm sorry it's getting so messy, but in these open spots, what do I place there? I'm going to place zeros, okay? And so to write this number a lot more cleanly, it's going to be 654 with 5 zeros. And so it'll look something like this, 65,400,000, all right? And again, we'll practice this a little more in class, but I'm assuming this is a bit of review for you guys. That actually takes care of this video. I will see you guys next time.